Welcome to my research presentation for my honors capstone, which is part of my engineering honors program. My name is David Lee, and my project is about modeling, controlling, and flight testing of a small quadcopter. So I want to start by describing how I got involved in this project. I have always been interested in mathematical precision, and there's a lot of great EECS classes out there. You know, great engineering applications, great professors, but they're sloppy. I find that a lot of EECS professors are more big picture oriented, but I care about the small pictures just as much as the big ones. So in fall 2020, I met this EECS 460 professor who was actually the exception. His course notes struck me as extremely precise and organized, and in fact, I appreciated the mathematical precision of the concepts in the class so much that I felt compelled to go into the field of control systems in grad school. So I reached out to this professor, Professor Seiler, hoping to gain research experience with him, and I was fortunate enough to have him be my faculty advisor for advanced directed study. And in this study, I incorporated EECS 460 concepts and explored the limits of tracking the altitude of a quadcopter, which eventually led to my capstone proposal of modeling, controlling, and flight testing of a quadcopter. So the first part of this project is to understand and model the physical dynamics of a quadcopter. A quadcopter has 4 rotors, 2 of which spin counterclockwise and the other 2 of which spin clockwise. There are 4 elementary motions of a quadcopter: vertical movement, roll movement, pitch movement, and yaw movement. To increase the altitudes of a quadcopter, for example, we will increase the speeds of all 4 rotors simultaneously. But to increase the roll of the quadcopter, we will increase the speeds of the rotors number 3 and number 4, and decrease the speeds of rotors number 1 and number 2. Similarly, to increase the pitch of the quadcopter, we will increase the speeds of rotors number 1 and number 4 and decrease the speeds of rotors number 2 and number 3. And finally, to increase the yaw, we will increase the speeds of rotors number 1 and number 3 and decrease the speeds of rotors number 2 and number 4. So that's a lot of numbers, but I hope you're not lost yet, because that's actually what I just described was a simplistic qualitative model for the motion of the quadcopter. We need a quantitative model, which is much more complicated, and because it involves external forces, angular momentum, and so on, which are impossible to describe verbally. But thankfully, the quadcopter I work with, which is called Parrot Mambo Mini Drone, has MATLAB and Simulink support. So this model I'm showing here is very powerful, but at the same time, very complicated. But after that first semester of advanced directed study, I was able to master how to perform complete simulations with the model. So I would give the input and obtain the output. So after figuring out how to perform simulations with the model, the next step is to control the quadcopter. And in the interest of applying EECS 460 control theories and gaining hands-on experience with controller tuning for a real application, I performed PID tuning for all 6 controllers, one at a time: altitude, yaw, roll, pitch, X, and Y. Note that because there are only 4 elementary motions of a quadcopter, we only end up with 4 overall outputs: pitch torque, roll torque, yaw torque, and total thrust. These are then converted into motor commands, which are then used to simulate the motion of a quadcopter. So for most of this project, up until February this year, I worked exclusively in the Simulink environment. I came up with various testing scenarios for evaluating the quadcopter's performance with the current PID controllers. For example, for evaluating the altitude performance of the quadcopter, I started with what I call the constant altitude scenario, where the altitude reference is constant and non-zero throughout the simulation, but all the other references are constant and 0. With progressively complicated scenarios such as the piecewise altitude scenario I'm showing here, and constant altitude and then linear yaw scenario, I optimized the controllers by hand to strike the balance between the speed of response and the amount of overshoot and oscillation. And in general, we want the speed of response to be as fast as possible and the amount of overshoot and oscillation to be as small as possible. So after I achieved a completely satisfactory performance of the quadcopter in simulation, I obtained the physical quadcopter from my advisor in February. But getting it to connect to my computer and the Simulink model turned out to be a significant challenge. There were so many roadblocks along the way that I had to overcome pretty much all by myself. But in the end, it's a great feeling to finally understand all the practical subtleties and be able to send flight code from the computer to the quadcopter. However, the initial testing of the quadcopter in practice was mostly an absolute disaster. I had countless stressful experiences of witnessing the mini drone fly straight up and hit the ceiling or do something completely crazy in the air and then crash into the wall or floor. I didn't want the drone to be destroyed by me. It turned out that the Simulink model was way too ideal and the controllers I tuned were simply impractical for the real quadcopter. Therefore, I actually had to revert back to the default controllers, those that came with the model. With those default controllers, the performance was now basically sometimes crazy instead of always crazy. Thankfully, at this point, I was familiar enough with the model to know that the issue must lie in the state estimation process. So I went ahead and experimented with various modified schemes of converting the sensor measurements into state estimates. And eventually, I got it to work for at least the altitude scenario. So here's an example of the quadcopter's final performance that I achieved. Here, I'm having the quadcopter take off and then stay at 0.7 meters for 15 seconds and then land. So that's what I was able to achieve over the course of this honors capstone. However, this project is actually my long-term research project. So I will still be working on it for the next year, my 5th year. That is my super senior year. At the beginning of this honors capstone, I set out with the goal of completing an S-shaped trajectory back and forth with the quadcopter in a lecture room. But as it turned out, just getting the quadcopter to take off and stay up there for 10 seconds in a stable fashion and without drifting away or anything could be extremely challenging in practice already. So I will continue to explore ways of improving the performance. For example, recently I discovered that during the initial transient period of the flight, the sensor measurements were very unreliable. So I came up with this experimental logic of not using the sensor measurements for altitude estimation until after the first 0.8 seconds. My other ambitions include deploying image processing algorithms in real time with a quadcopter, like having the quadcopter follow an object below it. In fact, I took X351 concurrently with this Capstone project. And in my 351 project, I worked on image processing with this exact same quadcopter that I'm talking about here for my Capstone project. So feel free to check out my X351 project website. Finally, I would like to thank my faculty advisor, Professor Peter Seiler. It was his precise and organized course notes, X460 course notes, that sparked my interest in controls. And without his agreement to supervise me for advanced directed study, I wouldn't have come up with this quadcopter project. In fact, it would have been impossible for me to do any testing in practice at all without Professor Seiler, because the Parrot Mambo mini drone has long been off the market, and I would have had no physical drone to test with. So that's the end of my presentation. Thank you so much for watching, and feel free to reach me anytime by email at davidlxl@umich.edu.